Okay, for the past couple of videos we've been speaking about the motor effect. In the motor effect, the field was already there and there was a current that was flowing through the wire, and because of the field that was created by the current wire interacting with the permanent field, the force was produced on the wire. So that's why there's a force there, and we use Fleming's left-hand rule to figure out the direction of the force. Now what we're going to talk about is electromagnetic induction. In this case, there's a field already there as well, but there's no current yet, and it's actually us who's going to apply the force. We're going to move the wire in or out of the field, cutting the field lines, and this will induce an EMF which will produce a current. So as you can see, in electromagnetic induction we're producing a current or inducing a current, while in motor effect the current was already there and we produced a force. Okay, here we have a magnet moving into a coil, and every time it moves into the coil you can see an EMF is induced, and when it moves out an EMF is also induced but in the opposite direction. So firstly, to figure out how much EMF is induced, we can use Faraday's law. Faraday's law says that the EMF induced is directly proportional to the rate of change in magnetic flux linkage. So the EMF induced doesn't depend on the magnetic flux linkage itself, it's about how quickly magnetic flux linkage increases or decreases. So if you look at it very carefully, when the magnet is actually inside the field, or when the magnet is not moving at all, there's no EMF induced. For example, right now, wait for a minute, you can see it's already there. There's a lot of magnetic flux linkage going through it, but there's no EMF induced. So it's only when it's moving in or out of the coil. Alternatively, you could actually move the coil and keep the magnet at the same position. It's about how quickly the flux through it is changing. This is the equation here. So EMF induced is proportional to the rate of change in magnetic flux. So change in flux divided by change in time, and because the number of coils doesn't really change, so it's on the outside. We can figure out the direction using Lenz's law. Lenz's law states that the direction induced is always such as to oppose the change that causes the current. So basically, if you're trying to if the magnetic flux is increasing through the coil, what happens is the coil will induce a current which tries to resist that change. So it's almost like the coil doesn't want the magnetic flux through it to increase, so induce a current in the opposite direction, try to oppose that increase. While if the magnetic flux is decreasing, actually it doesn't want it to decrease, so it induces an EMF in the opposite direction. Lenz's law shows itself as a negative sign in front of the equation there. Okay, so in this case what we have is we have a coil there, a square coil moving into a B field of uniform flux density, and what we're going to do is we're going to plot a flux linkage against time graph first. It's going to be very useful. So at the beginning, very beginning, the square coil is outside the field, so the magnetic flux is 0, and because it's moving at a constant rate into the field, the magnetic flux linkage is going to start increasing slowly at a constant rate. Okay, and then once the coil is inside the field, like this, the magnetic flux linkage is constant. It's already at its maximum and is constant until it starts to leave. And when it starts to leave, the magnetic flux linkage is going to start to decrease at a constant rate again. And then eventually, once it's outside of the magnetic field again, the magnetic flux linkage will be 0. So we can use this flux linkage against time graph to determine the EMF against time graph. That's because EMF is proportional to the rate of change of flux, and then there's a negative for the Lenz law. So we can actually use a gradient from this graph here to figure out this graph. So let's look at this at the beginning. So at the beginning, when the coil was outside the field, there was no change in the magnetic flux, so there was no EMF induced. And then as it started to move into the field, there was a change in flux, and we can figure out the gradient from this one, and you can see the constant gradient because the flux was increasing at a constant rate. But because it's a positive constant gradient and there's a negative sign in from Lenz's law, we're going to draw a constant negative voltage induced. But then once it's inside the field, you can see the magnetic flux linkage is constant. It's there, but it's constant. So now the gradient here, or the change in flux once it's inside the field, is 0. So the flux EMF induced is 0 until it starts to leave. And when it starts to leave, the flux linkage is decreasing. So it's a negative gradient over here. Because it's negative, but then Lenz law introduced another negative, which makes a constant positive gradient. So it's a constant positive EMF induced. So you can link them up like this. You can see every time there's an increase or decrease in flux linkage, there's a pulse showing that EMF is induced. And obviously once it's outside, there's no EMF induced.